Hello everyone, I am Mohammed Chaben, a PhD student at Colorado State University. This is a joint work with Aurora and Uber ATG. In this work, we present a joint detection and tracking approach called DEFT or Detection Embeddings for tracking. Tracking by detection leverages the power of deep learning based object detectors and is currently the dominant tracking paradigm. The recent trend of jointly learning detection and tracking tasks in a single neural network has led to increases in performance in tracking benchmarks. The proposed approach DEFT follows the tradition of recent works. In the next slides, we will show its advantages over the previous works. So, given the tracking by detection paradigm, we propose to exploit the representational power of the intermediate feature maps of the object detector backbone to extract embeddings to be used in an object matching network that associates objects across frames. DEFT is simple and lightweight. We show that it can be added to a number of detection backbones to provide effective joint detection and tracking with real-time throughput. An illustration of DEFT training is shown in Figure 1. The embedding extractor extracts representative embeddings from multiple feature maps of the detector backbone, and then the obtained appearance embeddings from the two input frames are then passed to the matching head, which estimates the similarity scores between all pairs of detections across the two frames. More details about DEFT training can be found in the paper. For matching estimation, we use a loss function that is symmetric in time. The matching loss Lmatch is defined as the average of the two losses Lmatch forward and Lmatch backward, as shown in equation 2, where Lmatch backward is the error of matching bounding boxes in frame t to those in frame t minus n, and Lmatch forward is the error of matching bounding boxes in frame t minus n to those in frame t. This formulation provides additional robustness to DEFT. DEFT is trained with the joint detection and matching losses, and we also use learnable parameters lambda 1 and lambda 2 as balancing weights between the detection and matching losses as shown in equation 3. During inference, the embedding extractor head uses feature maps and bounding boxes from the detector as input and extracts appearance embeddings for each detected object. The matching head uses the embeddings to compute similarity between the objects in the current frame and those remembered from previous frames. A key feature in DEFT success is that it keeps a long enough memory of appearance embeddings over time, which helps it to overcome the failings of the local regime methods and makes it more robust to occlusions and large interframe displacements than the top alternatives. A motion forecasting module is also used to prevent matches that lead to physically implausible trajectories. More details about DEFT inference can be found in the paper. We evaluated the performance of DEFT on a set of popular benchmarks, including KITTI and nuScenes. KITTI is used to evaluate 2D visual tracking, while nuScenes is used for monocular 3D visual tracking. For nuScenes, the videos are sampled at 12 frames per second, but frames are only annotated at 2 frames per second. So only keyframes are used for training and evaluation of DEFT and other approaches as well. The low frame rate of 2 frames per second makes nuScenes dataset challenging for visual tracking, as the interframe motion of objects can be large. DEFT was trained and evaluated with 4 object detectors. In Table 1, we show the threefold cross-validation results of implementing DEFT with different object detector networks on KITTI. DEFT plus CenterNet variant was the strongest in terms of MOTA accuracy. That's why it is used in all experiments of this work. But these results demonstrate that DEFT can achieve good tracking performance using different detector backbones. DEFT plus CenterNet variant runs at approximately 12.5 Hz on all datasets. Here we show comparison with state-of-the-art methods on KITTI and nuScenes. On KITTI dataset, DEFT achieves comparable performance with CenterTrack. Both CenterTrack and DEFT use a CenterNet detection backbone. This shows the power of the CenterNet detection backbone and provides support that the jointly optimizing detection and tracking methods can outperform those that have detection as a distinct step. We observe a big performance advantage with DEFT on nuScenes. Compared with CenterTrack, DEFT achieves gain of 13.1 percentage points in a MOTA, 25.3 in MOTA R, and 11.3 in MOTA. Here we show few qualitative examples for 3D tracking on nuScenes. In nuScenes, 7 object classes are used for tracking. We can see that even with the very large interframe displacements between consecutive frames and with the presence of multiple examples of heavy occlusions, DEFT is able to keep correct identities. As we saw 2 slides ago, DEFT and center track perform similarly on KITTI, but DEFT outperforms center track and all other methods on the nuScenes leaderboard by a large margin. Our intuition is that the major performance gains on KITTI are based on improved detectors, so the tracking logic can be weak and still produce top numbers. The authors of Tractor and Center Track seem to agree with that. However, is tracking without bells and whistles sufficient for harder tasks? That's why we decided to investigate that by proposing a way to judge the difficulty of the tracking scenes using an occlusion, a displacement, and a combined score for each video. In Figure 3, we show a comparison between DEFT and center track on nuScenes validation videos according to difficulty factors. We can see that the difference in performance between DEFT and center track is small on easier videos with respect to the displacement and the mixed difficulty factors. Interestingly, center track outperforms DEFT on the easiest videos of the mixed difficulty factor by less than 1 percentage point, which is consistent with the difference in performance we observed on KITTI benchmark. However, when looking at moderate and hard videos, we observe that DEFT provides better performance. We can see that for occlusion, for example, center track drops by around 8 percentage points from easy to hard, while DEFT drops only by 3 percentage points, which indicates that DEFT is more robust to occlusions than center track. And same conclusion can be made with respect to the displacement factor as well. In Table 2, we show ablation study of DEFT on KITTI and nuScenes datasets. Interestingly, we can see in the first row that a simple motion model plus IOU association step performs reasonably well in KITTI validation data, but fails to perform well on the more challenging nuScenes data, which validates our hypothesis that a strong detector plus weak association is able to perform well on KITTI. The next row shows the benefit of the multiscale learned embedding and the value of adding motion forecasting module. On KITTI, the naive baseline performs well enough that additional gains from DEFT results in cumulative benefit of only a couple percentage points across most metrics. On the other hand, on nuScenes, the value of DEFT is obvious. The gains in EMOTA from baseline to multiscale DEFT is over 14 percentage points, and this confirms that the learned matching based association step is critical to the overall performance on nuScenes. The code of DEFT is publicly available on this link. Thank you.